Okay, so it's time to start. I guess it's 11:15, so it's my turn to talk now. The test tomorrow is for 90 minutes, so you should have enough time. There will be questions of all kind, so both true, false, as well as you have to do some manipulations or computation. You really don't need any calculator. I mean, you can bring one, it's up to you. You can program it as much as you wish. But you should not have your laptop with you though. What else? Do you have any questions about the test? I mean, of course, I cannot tell you what is on the test because I don't remember myself. Yes?
Is it possible to come like 15 minutes early to start if you're supposed to be somewhere by 7 o'clock?
Oh. How many of you have that issue?
Just me.
Or just you?
No, ceremony is supposed to be at. I can see if I can work it out. It's just this other thing is planned many months ahead of time. So.
Okay. And so if you can't, let me know and then maybe we will work something out.
Okay.
Any other question? Yes?
Is this going to be about the same way? Or is it going to be a longer test because we have more time to work on it?
Of course it will be a longer test. Come on. No, I mean, longer doesn't mean, I really don't know how to define the length of a test. I mean, there will not be as many as true false questions as you had last time. Like last time it was worth 70 points. And this time it will be worth less than 70 points, which could be 69. No, no, I'm just kidding. It's not 69, but it's less than that. But I think the reason you have more time is because you may have to think a little bit more. And you have more material too. But it's very hard to say that the time duration you are being given is proportional to the length. I do not know what is the length of a test. I cannot measure it in meters, so I really don't know. And each one of you will take different amount of time. So if you get done early, that doesn't mean you made a mistake. It just, okay? Or if you need more time, that doesn't mean that you have made a mistake. So I really don't know, Michelle, how to answer that question. But it will take some time. Like, okay, if you have 90 minutes given, it may take anywhere between 50 and 60, or in some cases maybe more. So it depends how well you are prepared and how familiar those questions are to you. So it's an individual situation rather than saying all of you will need more time or all of you will need less time. So it's certainly not 2 + 2 = 4. Okay. The questions are from continuum mechanics. All of the material has been covered in the class. I don't know what else can I say. I think I just became a little bit over generous in the spirit of Thanksgiving. It was 75 minutes, so I made it 90 minutes. Either I made a mistake or not, I don't know. But it was designed for 75 minutes. Yeah, okay. No, originally it was designed for 75 minutes. And then when I checked it this morning, just before coming to the class, it says 5:30 p.m. to 7 p.m. So that's what we will do then. So it's for 90 minutes then. You can leave early. If you are done early, it's an upper limit, not a lower limit. Lower limit is 0, upper limit is 90. Anything else? Yes.
The teacher taught the classes, more extra classes.
So I was thinking of having one more like this. I was thinking of having a class on Thursday. But if you think you are tired of meeting on Thursdays, it's okay. I mean, it was meant to count as a class, yes. But now I guess you are asking me, will it count as a 2 classes or not?
It's close to it.
Yes, it is close to it, yes. So how many of you think, or how many of you vote that this should be counted, tomorrow's test should be counted as 2 classes? Okay, so we will not meet on Thursday. I guess Wake Forest people, you are with us, right? So there will be no class on Thursday.
Okay, we got that.
Okay, good. Any question you have from Wake Forest or Oak Ridge? I will email the test tomorrow morning to both Oak Ridge as well as Wake Forest, and you can schedule your times for 90 minutes. I realize Wake Forest students they have a heavy schedule tomorrow. So if they cannot take it tomorrow, that's okay. They can take it on Wednesday. Because they have many classes scheduled for tomorrow. So there is really no point in killing them or killing anyone. That's not the intention. So just because the test is for 90 minutes doesn't mean that it's either hard or easy. Okay, anything else? So what we were doing is we defined an isotropic material, and we said that for an isotropic material you can cut the specimen any way you like or in any direction you like, and if you do the same test on it, you should get the same result. In mathematics, that translates to rotating the reference configuration and then cutting the specimen along the same direction. For an elastic material, the free energy depends upon the deformation gradient F and the temperature theta. It cannot depend upon the gradient of theta because of the entropy inequality. And then we went through the fact that if you rotate the reference configuration and then do the test, you should get the same free energy as if you did the test on the unrotated reference configuration. And that required that phi really should be a function of B rather than F, where B is the left Cauchy-Green tensor. And then the objectivity requires, objectivity means you are rotating the present configuration. Material symmetry means you are rotating the reference configuration. So there's a difference between the two. So material objectivity requires that phi really should transform, that if you transform B by OBO transpose, the value of phi should not change. And that requires that this free energy should be a function of the 3 invariants of B. Invariants of B are the same as the invariants of C, which is the right Cauchy-Green tensor. And this relation we derived from the entropy inequality. That's the first Piola-Grkov stress tensor. And somebody reminded me that I should put tilde on it, so I have tilde on it. This was Francis who reminded me. So we have the first Piola-Grkov stress tensor. Now if you use the chain rule of calculus, so phi is a function of first invariant, second invariant, third invariant of B. And I mentioned, or I stated that there is a homework exercise which was not assigned to you, but it gives you the derivative of the first invariant with respect to F, the derivative of second invariant with respect to F, and the derivative of third invariant with respect to F. So if we substitute for these and use the fact, now I have skipped some algebra. If we substitute for Ti tilde, this is like first Piola-Grkov stress tensor, and use the relationship between Cauchy stress tensor and the first Piola-Grkov stress tensor, we come up with this relation. So that is the relation for a general elastic material. So this one, T, which I'm rewriting now, basically F0 identity plus F1B. The only difference is I'm not putting now indices, but it's the same relationship that we derived just last time. So F0, F1, and F2 are functions of first invariant, second invariant, third invariant of B and the temperature theta. Now if F1 equal to 0 and F2 equal to 0 and F0 is a function of, this Fn means function, is a function of B and theta. So it's a if statement, then we get T equal to F0 third invariant of theta, third invariant of B theta times identity. Now what is the third invariant of B? The third invariant of B is determinant of F, which is the deformation gradient square, which is the same thing as J square, J being the Jacobian or determinant of F. Now we know that rho J equals rho 0. Right? We know that rho J equals rho 0. That's the balance of mass. And we cannot violate that. So J is then rho 0 over rho. So T is F0 is a function of rho 0 over rho square times theta identity. And I see Ganesh doesn't like it. All I'm doing is substituting for the third invariant of B. And now I can use a different notation for this and call it a minus P all I'm doing is, see, rho 0 is a constant, that's a mass density in the reference configuration. So that doesn't, it's not a variable. So variable is rho. So I'm denoting F0, rho 0 over rho square theta, which is like F0 is a function of rho and theta. I'm denoting that by P now. How many of you think that you have seen this equation before? And I can assure you, you must have seen it before. Actually, I really have answered your question. So in a way, if I say raise your hands, all of you should raise your hands because all of you should have seen it. So where did you see it? How many of you took fluid mechanics? So you took fluid mechanics. So in fluid mechanics, what is an inviscid fluid? Non-viscous fluid. Eulerian fluid. Perfect fluid. You did not come across any one of those names? Eulerian fluid, perfect fluid, ideal fluid. So what was the constitutive relation for an ideal fluid? How many of you studied gas, say ideal gas? Come on, you cannot say you didn't study ideal gas. You did. So how many of you are familiar with this relation? PV equal to RT. That's the relation for an ideal gas. R is universal gas constant, T is the absolute temperature, P is the pressure, and V is the specific volume. So I can write this one as P over rho equal to RT. This T is absolute temperature. So it's really our theta. Our theta is absolute temperature too. right? So you said P equal to R rho theta. So that was the relationship for pressure in terms of the mass density and temperature. This one is a specific case of that. If I say P is a linear function of rho and theta, then I get this. If I say P is proportional to rho and P is proportional to theta, then I get this relationship because the constant of proportionality is R. So the ideal gas you studied or the ideal fluid you studied is a special case of a nonlinear elastic material for us. Right? So this, we can say that the ideal fluid is really an elastic material. Now, generally, all fluids are taken to be isotropic. So this relationship we derived is for an isotropic elastic material. And if F1 and F2 are zeros, then you get a relationship for an, either you can say an elastic material or you can say it's an Eulerian fluid. Okay, now, so let's assume we are still with this Eulerian fluid. So I get rho equal to P over R theta. So if you know the mass density, can you find the deformation gradient? Question is, if you know the mass density, can you find the deformation gradient? Is my question making sense? I mean, is it English-wise? You understand it, right? You know what I'm asking? Looking for F. Very good. So if you know rho, the mass density, which is, to give you a hint, which is really J, can you find F uniquely? No, there are so many F's that have the same determinant. So the implication is that this stress-strain relationship for a general elastic material is not solvable for strains. You cannot solve for strains in terms of stresses. You cannot invert this relationship and solve for B in terms of T. I just gave you a counterexample. The counterexample is when F1 and F2 are zeros, and F0 is a function of third invariant only. You solved for rho, but from rho or J, you cannot find F. F has 9 components, J is only one quantity. So knowing the determinant of a matrix does not give you the matrix. So for a nonlinear elastic material, for a nonlinear elastic material, the stress-strain relationship cannot be inverted. In the sense, you cannot solve for strains in terms of stresses. So it's one way. We express stresses in terms of strains, but we cannot solve for strains in terms of stresses uniquely. Okay, also, before I go further, this relationship, the stress-strain law, is generally written in a slightly different form, but which is equivalent to this one. And that is because of the following, Hamilton-Cayley theorem. Sometimes as Cayley-Hamilton theorem or Hamilton-Cayley theorem. Both are, these are two different persons. This theorem says that if this identity holds in a three-dimensional space, which means B is a 3 by 3 matrix, then b cube minus first invariant of b times b square plus second invariant of b times b minus third invariant of b times identity matrix is equal to 0. No matter which matrix you take, any 3 by 3 matrix you take, then any 3 by 3 matrix satisfies this identity or this relationship. So that's Hamilton-Cayley or Cayley-Hamilton theorem. Now our matrix B is invertible. It's a positive definite matrix. So you pre-multiply by B inverse. So we get B square then minus first invariant times B plus second invariant times identity minus third invariant times B inverse equal to 0. Oh, yeah. Pre-multiply by B inverse. Pre-multiply by B inverse. So this identity also holds. Solve for B square and substitute here. Solve for B square and substitute in the strain law. So what we get then is T equal to F0 times identity plus F1 times B plus F2 times first invariant B minus 2 times identity plus 3 times B inverse. Solve for B square and plug in there or substitute in there. So that's what we will get. Then we can combine this term with that because both are multiplying B. We can combine this term with this. Both are multiplying identity matrix. So what we get then is F0 minus second invariant times F2 times identity plus F1 plus first invariant F2 times B plus F2 third invariant B inverse. So F0, F1 and F2 are functions of, they are functions of first, second and third invariants of B and temperature theta. So if I combine these up, they still will be functions of first, second and third invariants of B and theta. So we call them, we just denote them by different symbol now. So that we can say, what symbol do you like, G or F? I think in the book I still have F0s. But it doesn't matter though, this is no different function. So it's say F0 hat plus F1 hat plus F minus 1 hat B inverse. So the first quantity in the parenthesis we are denoting by a different symbol, F0 hat. We are writing this thing with F0 hat, this one with F1 hat, and this one with F minus 1 hat. Now F0, F1 and F minus 1 hat, these are functions of first, second and third invariants of B and temperature theta. So the life is not any simpler than what it was before. To to define an elastic material, we really still have to do lots of experiments, because you have to keep first invariant, second invariant fixed, and then change the third invariant. Then keep first and third invariant fixed, change the second invariant. Then keep second and third invariant fixed and change the first invariant. And then fit a curve through them. So it's a lot of work. And I think if Fred, Jessica, and maybe Piers and Josh spent maybe 10 years each, we might be able to characterize one rubber, like one material or one tissue. Remember, we have to do lots of tests because there's a huge variation. We are talking about large strains. We are not talking about small strains. So also, these relations may or may not be invertible. So let's see what can we learn from these, or what should we be expecting. Now, as it stands, there is no guarantee that if you pull this specimen, say along 3 directions, if you pull this specimen along 3 directions, you will get equal stretches along 1 and 2 directions. There is no guarantee of that in this theory. It's possible that if you pull it along 3 directions, the strains along 1 and 2 directions are different. The theory does not rule that out. All it tells you is that this is the relationship between stress and strain for an isotropic material. Now, supposing I take let B be an eigenvector of this matrix B. Then so B1, so let's say equals lambda 1 B1. So that's the definition of an eigenvector, right? And lambda 1 is the corresponding eigenvalue. So lambda 1 is the corresponding eigenvalue. So what about the eigenvector of the Cauchy stress tensor T? So I'm trying to find what is TB1. So if we do that, we get F0 hat plus F1 hat B, this is identity, plus F minus 1 hat B inverse is operating upon B1. Josh, I think I lost you.
What's that right next to the F1?
Identity matrix. So we have F0 hat I operating upon B1 gives us B1. Identity matrix multiplying B1 will give us B1. Multiplying is not the right word, but operating upon B1 will give us the vector itself plus F1 hat B operating upon B1. So many of you are pointing towards the equation above it, so that's lambda 1 B1 plus F minus 1 hat. Now B inverse operating upon B1. 1 over lambda 1. So the eigenvalue of B inverse is the reciprocal of the eigenvalue of B, and they have the same eigenvector. So that will be 1 over lambda 1 times B1. B inverse operating upon B1 will give us 1 over lambda 1 B1. Oh, no, B1 is everywhere in all three terms. So what we get then is F0 hat plus F1 hat lambda 1 plus F minus 1 hat lambda 1 So what does it tell us? Yes? I think you should speak into that microphone.
T is equal to the first term there. F0 plus F1 plus F1.
So now, what can I say about the eigenvector of T? Yes?
B is an eigenvector of T.
So B1 is an eigenvector of T. So since we chose B1 and an eigenvector of B, and we can take another one, we will get the same result. So eigenvectors of B are eigenvectors of T. Eigenvectors of B are eigenvectors of T. So what did we call the eigenvalue of Cauchy's test tensor? What is an eigenvalue of Cauchy's test tensor equal to? Yes? Principal stress. Good. So this quantity is the principal stress. This whole thing is the principal stress. What is another name for eigenvectors of B? They are directions of, yes? Principal strain in the present configuration. How come he knows all the answers and other guys are not responding or gals are not responding? Eigenvectors of B are axes of principal strain, or those are the directions along which the axial strains are maximum or minimum in the present configuration. In the present configuration. So what it tells us is that the axes of principal strain in the present configuration are also axes of principal stress in the present configuration. Axes of principal strain in the present configuration are also axes of principal stress in the present configuration. Does it make sense? How many of you think that I said axes of principal stress are also axes of principal strain? How many of you think that I said axis of principal stress are also axis of principal strain in the present configuration? Did I say that? I did not say that. Okay? That statement is not necessarily true. The reason it is not true is that we go back to this example problem, which is an elastic material. And here, what are the principal axes of stress? What are the principal axes of stress for this material? Ashley, at Wake Forest?
I don't know.
Ganesh? Every direction. Every direction is a principal axis of stress. What about principal axis of strain? We don't know, because we don't know B. We cannot find B even uniquely. Okay? First of all, I cannot invert it. Even if I can invert it, for a perfect fluid, I can, like ideal gas, I can invert it. But all I get is mass density, which gives me J. J does not tell me anything about F or B. So principal axis of strain, even though principal axis of strain or principal axis of stress for an isotropic material, the converse may not be true. May not. I did not say will not. There's a difference. Right? So the converse may not be true. But by that what I mean is in some cases the converse is true. In general it is not true. Okay, now our friend does experiments, and let us see what can we say about the reference configuration. So this is the material. This is our isotropic elastic material. And we are assuming that the material is the body is homogeneous, which means each material particle is made of the same material. So in the reference configuration, what is B? What is the value of B in the reference configuration? Josh? Identity matrix. So what is the first invariant? 3, sum of the diagonal terms. Second invariant is also 3. Third invariant is 1. And let's assume the temperature is uniform. Let's assume that the temperature is uniform, like it's the same everywhere. Then the Cauchy stress tensor is 3, 3, 1. It's a function of first invariant, second invariant, third invariant, and temperature. Plus F1 hat B plus F minus 1 hat B inverse, which is also identity matrix. Inverse of a matrix, inverse of an identity matrix is an identity matrix. So let's call it alpha tilde times identity. Alpha tilde is a constant now. So what can be the state of stress in the reference configuration of an isotropic body? What can be the state of stress in the reference configuration of an isotropic body? What kind of stress state can we have in the reference configuration of an isotropic body? Yes, no. It's hydrostatic pressure. It's hydrostatic pressure. If you have anything other than hydrostatic pressure in the reference configuration, the body cannot be isotropic in that configuration. So you cannot, Fred is thinking, the samples he tests, of course he tests composites with laminas. In that, this theory does not apply. All it says is, if the first of all, if alpha hat is a constant, then since you have a free boundary, on the free boundary, Tn must be 0. That's the boundary condition. So if alpha is a constant, he has an appointment somewhere at 12:15. He told me. So class is not over yet. He has to go across the campus. Okay, so if on the boundary there is no load applied or no traction applied, then Tn is 0. And if alpha is a constant, then alpha hat must be 0. So that means there should be no residual stress in the body. See, if the residual stress in the body is not a hydrostatic pressure, if the residual stress in the body is not a hydrostatic pressure, then the body is not isotropic in that configuration. Okay, now some of you are still wondering, how do I get Hooke's law from all this stuff? Okay. So that's the next goal. How do we get Hooke's law from whatever we have studied for an isotropic material? How many constants are for an isotropic material? How many elastic constants or material parameters are for an isotropic linear elastic material, Hookean material? 2. Young's modulus and Poisson's ratio, or Young's modulus and shear modulus, or Young's modulus and bulk modulus. So let's do that. So now let's talk about small deformations. Infinitesimal deformations. So F, the deformation gradient, equals identity plus the displacement gradient. And deformation small means the magnitude of H is much less than 1. The magnitude of each component of H, there are 9 components. The magnitude of each component is less than 1, much less than 1, so that H square is negligible as compared to H. Okay? So what's B? B is FF transpose. So that will be identity plus H, identity plus H transpose. And if we expand it, we get identity plus H plus H transpose. That's up to the first order term. We did not keep the H square term. B inverse is identity minus H transpose. Again, approximately. We are not keeping the second order term. So you can say we are taking the inverse of this. Third invariant, which is determinant of B, which is determinant of F squared, which is determinant of 1 plus H squared because determinant of F transpose is same as the determinant of F. So third invariant is determinant of B, which is determinant of F times determinant of F transpose, which means the same thing as determinant of F squared. And if you expand this, you get 1 plus trace of H. Trace of H means H11 plus H22 plus H33. Trace means sum of the diagonal terms. The trace means sum of the diagonal terms. Okay? Does anyone remember what is this equal to? H plus H transpose. This is twice of the small strain tensor. So we wrote half of H plus H transpose is the infinitesimal strain rate tensor, infinitesimal strain tensor. So this is identity plus twice of E. This is identity minus twice of E. This is 1 plus trace of E. Trace of E means E11 plus E22 plus E33. Okay, what about the first invariant? First invariant is trace of B So trace of B, so to the first approximation, what is trace of 1? Trace of 1, 3. So that's 3 plus twice trace of E. It's from here. Take the trace of both sides. Second invariant is this 1/2 trace of B square minus trace of B square. And if we find this, this also comes out to be 3 plus a number here which I don't remember times trace of E. There is a sum multiplier here. It could be 2 or 1 or 3, I don't remember. There's a number here, like could be 1, could be 3, could be 2. So there's a number here which I don't remember. Okay, this is not exactly like I'm missing a factor of 2 or 3 or 5 or something like that. Not 5. It's most likely 2. It's most likely 2, but anyway, okay. So now I have F0 as a function of first, second, third invariant and temperature. We expand this in terms of Taylor series about the reference configuration. Expand this in terms of Taylor series about the reference configuration. So we get in the reference configuration, this is 3, 3, 1 and theta 0. Plus differentiate this with respect to the first invariant, Taylor series expansion. Evaluate this in the reference configuration, which means 3, 3, 1, theta 0, and the first term will be I minus 3. Plus differentiate with respect to the second invariant, evaluate in the reference configuration. So second invariant minus 3 plus delta F0 or delta third invariant, evaluate in the reference configuration. So third invariant minus 1 plus delta F0 over delta theta. Yes?
In the book you have
raised the second order.
So this factor is 4. Good, thank you. That question mark I had is really 4. And the other terms will be quadratic in H. There will be, I mean, this is Taylor series expansion, so this is really, there are many terms, but the remaining terms are H, they involve H square. So we don't keep them. Yeah, I'm looking at the clock. Okay. Now, so we go back and substitute in this equation. Substitute for F0 hat, do the same thing for F1 hat, do the same thing for F minus 1 hat, and we come up with the following. Now this, you have to do the algebra to believe it. So the result will be the following then. T equals some constant alpha times theta minus theta 0 times identity alpha is some constant. It's not equal to the coefficient of thermal expansion. It's really stress temperature modulus plus lambda excuse me, some constant lambda times E kk times identity. E kk is same thing as trace of E. This thing is same thing as trace of E. Plus twice mu times E. Lambda, mu, and alpha are constants. These are some combinations of delta F0 over delta I on first invariant, delta F0 over delta second invariant, some combination of those. So if you combine the terms, you end up with this. And if the temperature is kept uniform, there is no change in temperature, then if there is no change in temperature, this term drops out. If there is no change in temperature, this term drops out, and you get what you are looking for or what you have been using. And this is Hooke's law. There are only two material parameters, lambda and mu. There are only two material parameters, lambda and mu. Okay. And that's the lowest we can get. And that's the simplest we can get. Which one do you want? This one?
The top line.
Which one? This one?
Yeah.
Okay, so just make a guess. If I had kept the quadratic terms, I will quit after you answer that guesswork. If I had kept the quadratic terms, which means H square terms, and temperature were uniform, how many constants will we get? Oh, come on. It's an isotropic material. So if I had kept the second order terms, how many constants will we get? See, we have a tendency to keep on like E squared, like add the E squared term. But if I had gone through this expansion the way we did it and had kept the second order terms, how many constants will we get? So I was, well, okay, 6. So you cannot just add one more term and say we are done. You will get 6 constants. Okay? So if you do systematically, keeping first order terms, and here we have assumed the initial configuration is stress-free. So if E is 0, so there's another assumption made here. Otherwise you won't get this one. You will get, we are assuming that T is 0 in the reference configuration. I'm not sure if I will be doing that in the class, like on Wednesday, to keep the second order terms, but I can give you the relationship though. That if you keep the second order terms, then it matters which stress tensor you are talking about also. In the first order theory, the one we are doing here, it does not matter whether you are talking about Cauchy stress or first Piola-Kirchhoff stress tensor or the second Piola-Kirchhoff stress tensor. But in the second order theory, it matters. Okay, thanks. So I owe you 5 minutes. Okay.
So do we have 6 more?
No, 6 total. 6 total. Not 6 more, 6 total. Okay, so I will give you back 6 minutes either next time or on Friday.
Dr. Batra,
Yes?
were you going to give us the homework even though it wasn't assigned? I think you had said last week you were going to give it to us so we could see what type of questions would come from that part of the chapter.
Sorry, hey, please be quiet. Oh, I cannot listen to the question. Please repeat your question.
I was just wondering if you were going to email out the homework that you didn't assign so that we could see what type of questions were coming from that part of the chapter. You had mentioned that last week.
Yeah, the questions will not be from that homework. I think what she's asking is, can I email the last homework? And my problem is my assistant Norma is not here, so I really can't get anything typed. So, but the question on the exam will not be related to whatever is on the last homework problem.
Okay.
Pardon me? You have one. I will give you homework on Wednesday maybe. In terms of the test, you have everything you need. In terms of the test, I have returned all the homeworks except the one you just gave me, which is not related to the test because it has nothing to do with the homework. Right?